In this video, we review the work on 3x3 matrices for Unit 4 of the Further Maths specification for the Welsh Joint Board. So, we need to be able to calculate the determinant of 3x3 matrices and also interpret the determinant as a scale factor for transformations, and also something that gives us information about the orientation of the image compared to the orientation of the object. And we need to have a method for calculating the inverse of 3x3 matrices using the cofactor and adjugate matrices. So for key facts, if we've got a 3x3 matrix, then the formula for the determinant is that rather messy one presented there, but in fact it's much easier to remember how to calculate the determinant of a 3x3 matrix. So you start off with the matrix, or the determinant to be calculated. You repeat the first two rows underneath, and then you use a process of diagonals. So first of all, we do diagonals from left down to right. So the first one is AEI, the second one is DHC, and the third one is GBF, and they're the three positive terms in the determinant. And then we do the same thing with the negative direction, or going from top right down to bottom left. So the first one is CEG, second one is AHF or FHA, and the third one is IBD. And those, of course, are the three negative terms in the determinant. So if we add up the result of the three positive diagonals, add up the result of the three negative diagonals, and then the final value of the determinant is simply P minus Q. And that means we haven't got to remember the complicated formula for the determinant. The process of finding the inverse of a 3x3 matrix is quite complicated. You first of all find the cofactor matrix. And to do that, you start off with this grid of plus, minus, plus, minus, plus, minus, plus, minus, plus. And then taking each entry of the grid in turn, you delete the corresponding row and column of M. You evaluate the determinant of the remaining 2x2 matrix. And finally, if the grid entry is positive, then you replace it with the determinant. And if the grid entry is negative, then simply replace it with -1 times the determinant. The adjugate matrix is simply the transpose of the cofactor matrix, and that is the first row of the cofactor matrix becomes the first column of the adjugate matrix, the second row of the cofactor matrix becomes the second column of the adjugate matrix, and the third row of the cofactor matrix becomes the third column of the adjugate matrix. And to find the inverse matrix of a 3x3 matrix, then we first of all calculate the determinant of M. If the determinant of M is 0, then the matrix M does not have an inverse, and M is said to be a singular matrix. If the determinant of M is not equal to 0, then M does have an inverse, which is given by 1 over the determinant times by the adjoint. And in that case, we would say that M is a non-singular matrix. If we have a transformation which takes the point xyz to the point m times xyz, then the determinant of M gives us a volume scale factor for the transformation. In other words, the volume of the image is the modulus of the determinant times the volume of the object. Moreover, if the determinant of M is negative, then the orientation of the image will be in the opposite direction to the orientation of the object. And if the determinant of M is not equal to 0, then the inverse matrix exists and is the matrix that gives the inverse transformation that takes image points back to object points. So we'll now move and start having a look at some examples. So the first one's taken from a 2012 paper. We have the matrix A. We've got to first of all show that A is non-singular for all values of k. And then in the case when k equals 3, we have to find the adjugate matrix of A and also find the inverse matrix of A. So we've got to show that A is non-singular for all values of k. We must remember that non-singular means that it has got a determinant which is not equal to 0. So we've got to work out the determinant of A. So to work out the determinant of A, first of all, repeat the first two lines underneath. And then we'll start looking at the positive diagonals. So the first positive diagonal is k times 1, which is k squared. The second positive diagonal is 1 times 1 times 6, which is 6. And the final positive diagonal is 0 times 1 times 4, which is 0. And now we must move our attention to the negative diagonals. So the first negative diagonal is 6 times k times 0, which is nothing. The second negative diagonal is 4 times 1 times k, which is 4k. And the final negative diagonal is 1 times 1 times 1, which is 1. So the value of the determinant is k squared plus 6, take away 4k plus 1, which simplifies to k squared minus 4k plus 5. Now we want to show that this is non-singular for all values of k, so we want to show the determinant is non-zero for all values of k, and the easiest way of doing this is to complete the square. So the determinant of A can be written as k minus 2 squared plus 1. K minus 2 squared is always at least 0, so the value of the determinant is always at least 1. The determinant cannot be equal to 0, so the matrix A is non-singular for all values of k. Moving on, we've now got k equals 3, so our matrix A has a first column of 3, 1, 6, a second column of 1, 3, first row of 3, 1, 6, a second row of 1, 3, 4, and a third row of 0, 1, 1. So to find the adjugate matrix, we first of all have to find the cofactor matrix. And to find the cofactor matrix, we need to start off with this grid of pluses and minuses. Taking the top left-hand entry, deleting the row, and deleting the column corresponding to that entry, we're left with the 2 by 2 matrix, 3, 4, 1, 1. The determinant of that is 3 times 1, take away 4 times 1, which is minus 1. The entry in the grid is a positive, so we simply put the minus 1 in as our first entry of the cofactor matrix. So we've now got the minus 1 replacing the first entry in the grid. So let's now move on to the second entry in the top row. Cross out the corresponding row and the corresponding column. We're left with the matrix 1401. Work out the determinant of that. 1 times 1, take away 4 times 0 is 1. The entry is a minus in this case. So the entry in the grid matrix is a minus. Therefore, what we've got to put in is the negative of the determinant. In this case, we've got to put in an entry of -1. So we now need to move on to the third entry in the first row. Cross out the corresponding row, cross out the corresponding column, work out the determinant of what's left. We've got a positive in the grid matrix, therefore the entry is just going to be the same as the determinant, which is going to be 1. Moving on to the first entry in the second row. The determinant of what is left is 1 times 1, take away 6 times 1, which is -5. The entry in the grid matrix is a minus, so we are going to multiply the determinant by -1 to get +5 as the entry. So we've now reached that stage. Moving on to the second entry in the second row. The determinant of what is left is 3. The entry in the grid matrix is a positive, so the entry in the grid matrix is going to be replaced by the determinant, which is just 3. Moving on to the final entry in the second row, same thing again. Determinant of what's left is 3 times 1, take away 1 times 0, which is 3. However, the entry in the grid matrix is a minus at the moment, so we've got to take the negative of the determinant. So the entry going into our cofactor matrix is going to be -3. Moving on to the first entry in the final row. The determinant of what is left is -14. In the grid matrix, we have a positive, so the entry is going to be the same as the determinant, which is -14. Into the second entry on the final row, the determinant of what is left is 6. The entry in the grid matrix is a minus, so what we're going to put into the cofactor matrix is the negative of the determinant, in other words, -6. And the final entry of the cofactor matrix now, the determinant there is 8. The entry in the grid matrix is a positive, so the entry in the cofactor matrix is just going to be the same as the determinant, that is 8. So we've got our cofactor matrix after all of that work. Unfortunately, that is most of the work. The adjugate matrix is the transpose of the cofactor matrix. So the first row of the cofactor matrix becomes the first column of the adjugate matrix. The second row of the cofactor matrix becomes the second column of the adjugate matrix, and the third row of the cofactor matrix becomes the third column of the adjugate matrix. So we've found the adjugate matrix, and now to find the inverse matrix of A, we simply have to remember that the inverse matrix of A is 1 over the determinant times by the adjugate matrix. We've got the formula for the determinant of A is k minus 2 squared plus 1. So when k equals 3, the determinant of A is simply going to be 2. And the inverse of A is 1 over the determinant times by the adjugate of A. So that is a half times by the adjugate matrix. And there's no need to push the half into the matrix. You can just leave it there. So let's now move on to a second example. We have matrices A and B given there. We have to evaluate the matrix A times B, and hence or otherwise we have to find the inverse matrix. A inverse. Okay, so part A, we've got this matrix multiplication to do. So we need to do our matrix multiplication. So if we take the first row of A and multiply it by the first column in B, we've got 3 times 3 is 9, plus 2 times minus 3 is minus 6, plus 4 times 0 is 0, so that's 9, add minus 6, add 0, which is 3 as the first entry in AB. If we now take the second row in A and multiply it by the first column in B, we've got 3 times 3, 9, added to 3 times minus 3, which is minus 9, added to 6 times 0, which is 0. So we've got 9, add minus 9, add 0, which is 0. And if we now do the third column in A, the third row in A, times by the first column in B, we've got 2 times 3 is 6, and we have to add 2 times minus 3, which is minus 6, and then we have to add 3 times 0, which is 0, so we've got 6, add minus 6, add 0, which gives me 0 again. We can carry on the multiplication process, and you can easily check the following figures yourself. And we see that the result of A times B is it's 3 times the identity. In other words, A inverse must be a third of B, because we've got A times B is 3 times the identity. A times A inverse must just be the identity, so A inverse can simply be a third of B. You certainly don't want to go through the whole cofactor matrix process to work out the inverse of A, having done the multiplication in part A. So let's see what else we've got to do with this question then. First of all, we've got to solve a set of simultaneous equations, and if you look carefully at these simultaneous equations, you will see that they are equivalent to the matrix A times by x, y, z equals 14, 18, 11. So we've got the matrix A times x, y, z equals 14, 18, 11. If we pre-multiply each side of the equation by A inverse, then we get A inverse A times x, y, z equals A inverse times 14, 18, 11. But A inverse A is the identity, and the identity times by x, y, z is just x, y, z. So we've got x, y, z is A inverse times by 14, 18, 11. We know that A inverse is a third of 3 minus 2, 0, minus 3 minus 1, 6, 0, 2 minus 3. And we have to multiply this by 14, 18, 11. And again, this is just a basic matrix multiplication. 3 times 14 is 42, add minus 2 times 18 is minus 36, add 0 times 11 is 0, so that's 42, add minus 36, add 0, which is 6, but I only want a third of that, so that's going to be 2. For the second entry, minus 3 times 14 is minus 42, together with minus 18 and 66. So I've got minus 42 plus minus 18 plus 66, which is 6. A third of 6 is again 2. And then the final entry, 0 times 14 is 0, 2 times 18 is 36, minus 3 times 11 is minus 33. So we've got 0 plus 36 minus 33, which is 3, and a third of 3 is just 1. So we've got x, y, z is 2, 2, 1. In other words, we've got x equals 2, y equals 2, and z equals 1. And then we have to find the matrix M, which satisfies m times a is 6 minus 3, 0, 0, 9, 12, 0 minus 6, 15. Well, let's write C for the right-hand side of this equation. So we've got the equation m times a has got to equal c. We want to find out what m is. So what we really need to do is we need to try and knock out the a. And we can knock out the a on the left-hand side by post-multiplying each side of the equation by a inverse. So we've got a inverse equals c times a inverse. A times a inverse is just the identity. So the left-hand side becomes m times the identity equals c times a inverse. M times the identity just gives me m. So I've got m equals c times a inverse. So to find out what m is, we simply need to multiply c by a inverse. Okay, so if you look at the first entry, so that's obtained by multiplying the first row by the first column. We've got 6 times 3 is 18, minus 3 times minus 3 is 9, and 0 times 0 is 0. So we've got 18 plus 9 plus 0, which is 27, and a third of 27 is 9. So our first entry is 9. If we do the second row by the first column, we've got 0 times 3, which is 0. 9 times minus 3 is minus 27. And then we've got 12 times 0 is 0. So we've got 0 plus minus 27 plus 0, which is minus 27. But then multiply that by a third, we've got minus 9. And we can carry on finishing the multiplication off just like that to obtain the final answer for the matrix M. And for our final example, we have a pyramid of volume of 20 units cubed. It's transformed by the transformation with matrix 3, 1, minus 2, 5, 1, minus 4, 3, minus 2, 1. We have to find the volume of the image of the pyramid and also comment about the orientation of the object pyramid and its image. Well, to find the volume of the image, we need to consider the determinant of the transformation matrix, because the determinant of the transformation matrix gives us the volume scale factor. So we know that the volume of the image is going to be the modulus of the determinant times by the volume of the object. So we need to work out the determinant of the matrix 3, 1, minus 2, 5, 1, minus 4, 3, minus 2, 1. So repeat the first two rows, go through the process of working out the positive diagonals. So we've got 3, then 20, and then minus 12 from the going down the positive diagonals. And then going down the negative diagonals, we've got minus 6 and 24 and 5. So the value of the determinant is 3 plus 20 plus minus 12. Take away minus 6, add 24, add 5. So the determinant is minus 12. So the volume of the image is going to be the modulus of minus 12 times by 20, which is 240 units cubed. And the fact that the determinant of the matrix of the transformation is negative tells us that the orientation of the image will be the opposite of the orientation of the object.